Isn't NASCAR just turning left? Any NASCAR fan would have your head for saying that. It's much, much harder. And we will not investigate those reasons in nearly enough depth. However, we're going to use some real NASCAR numbers to consider bank turns. All right, so one thing, Daytona International Speedway has really, really steeply banked turns, 31 degrees, really steep. And cars can take that turn at 200 miles per hour. And so we're going to analyze one particular turn on the Daytona International Speedway, which has a radius of about 985 feet, which conveniently is 300 meters. And we're going to try and drive our car around this 31-degree banked turn. So let's try this bank turn on an icy surface, one where there is no friction available. So if you were to try to drive this turn, let's make ourselves a little banked turn. And we've got our little dashed yellow line. So we've got a vehicle driving down, headlights coming right at us. If you were driving too fast, if you imagine have a bowl or some kind of a container with sloped sides, and you have a marble in there. If you spin that marble, if you start to spin it too fast, that marble is going to work its way up and out of the container. So if you're going too fast, you're going to end up going off the high side of the track. However, if you go too slow, if you're spinning around and you stop spinning it, friction is going to slow that marble down, and it's going to slow down. It's going to end up going down the track. So what we're looking for is the right speed. Like, what is the exact right speed to just maintain that spot on the sloped surface? So that's what we want to know. So we're going to start with our typical, FC equals mv squared over r. Like this is how we figure things out. Now we've got mg down, we've got a normal force in that direction, and I'm going to sort of draw this with a dashed line because the centripetal force is not actually a force acting on this. It's not a named force. It's the resultant of the normal and the weight force. In fact, because mg is straight down, the only contributor to centripetal force is the x component of the normal force. Normal force in the x direction is going to contribute to that, whereas normal force in the y direction is going to simply counteract gravity. So looking at this in the x and y directions. In the y direction, usually going to start there because it's arguably simpler. We've got the normal force in the y direction minus mg equals 0. What is the normal force in the y direction? If we look at this more closely, the angle of elevation is 31 degrees, and through geometry that I'm not going to delve into the details of, this angle right here is 31 degrees. I suppose you could say this is the surface. If I elevate this surface upward, the angle between my hands right here, as that angle decreases, the angle between the normal and the vertical will also decrease. So here's 31 degrees, and as it gets closer to 0, well, here's vertical, and as the slope gets lower, the normal force and the vertical get closer to 0. So those two angles are the same. So 31 degree elevation bank, 31 degrees between the normal and the vertical. So that tells us that the normal, the y direction is going to be the adjacent side of this normal force. Normal that way, normal y, angle here. So that means that the normal force times the cosine of the angle minus mg equals 0. So n cos theta equals mg. We'll plug in some values. Shortly. Oh, let's plug it in now. Since cosine of theta is known, well, we know the angle is 31 degrees. Cos of 31 is 0.86. So we've got 0.86 times the normal force equals mg. Normal force equals mg over 0.86. Just keep that there for a little bit. In the x direction, the only force contributing to centripetal is the normal force in the x direction. So we got normal force equals mv squared over r. Remember, the centripetal force is the sum of whatever forces are acting that result in centripetal motion, circular motion. In this case, there's only one, the normal x. So since the normal force is being measured against the vertical, the opposite side of that triangle is going to give us the normal force in the x direction. So that's going to be sine. So normal times the sine of theta equals mv squared over r. And we have an expression for the normal force. Let's plug that in. So we got, oh, you know what? I'm going to undo this. It's a little more elegant if we actually leave this as n cos theta. All right, forgot about that. Cos theta. So we plug in the normal force for here. We've got mg sine theta over cos theta equals mv squared over r. A couple things happen. One, masses cancel out. Yay! Another interesting thing happens. Sine theta over cos theta. If there's one trig identity that you memorize, it should be this one. Shows up generally more often than others. So g tan theta equals v squared over r. And we wanted to know v. What's the velocity that will let you traverse this bank turn with no friction? Let's solve for that. V squared equals r g tan theta, square root that whole thing. V is going to be equal to the square root of 300 meters times g, 10 times the tan of 31 degrees. So the velocity, 300 times 10 times tan of 31 square root is going to be 42.5 degrees. That's somewhat excessive. That is even steeper than 31 degrees. So arguably unrealistic. All right. Oh, momentarily forgot what I was doing. 42.5 meters per second. Got the wrong unit altogether. 42 meters per second. What is that in miles per hour? Let's convert meters, seconds. 42.5 divided by 1609 times 3600 is 95 miles an hour. You're not going to win any races doing that. 95 miles per hour. My Volkswagen can go 95 miles an hour. It's not going to win you a NASCAR race. All right. Suppose instead of needing to go the right speed, let's say we want to go NASCAR speed. We want to win this thing. We're going 200 miles an hour, 90 meters per second. What bank do you need? How steeply does this thing need to be banked in order to prevent you from sliding off the top? Well, it's the same setup, basically. We've got in the x, in the y direction, we've got the normal in the y direction, which, I'm just going to basically copy what we had from before. We're just working with different values. N cos theta minus mg equals 0, and cos theta equals mg, normal force, equals mg over cos theta. And in the x direction, we've got the normal force in the x direction equals mv squared over r, and sine theta equals mv squared over r. Sub this in, we end up with mg tan theta equals mv squared over r. M's cancel, but this time we're looking for the angle. So tan theta equals v squared over r g. Theta equals inverse tan of v squared over r g. All right, so let's plug those things in. Inverse tan of the 90 squared. Remember, we want to go NASCAR speed here. 90 squared over the radius, it's a 300-meter radius track, and g is 10. So the angle is going to be 90 squared divided by 3,000 inverse tan. It's going to give me an angle of 69.7 degrees. 69.7 degrees. That is talking about a track which is angled somewhere around this. You're going to put a car on that. If your car breaks down, you are sliding down that track into a ball of fire. You don't want that. So a 70-degree bank track, not quite so realistic. So if you want to win NASCAR races, let's spend money on tires. Sticky tires are the way to go. Let's use them. I'm going to copy this diagram because I like it a lot. I'm going to erase those normal forces because what I'm going to do is I'm going to copy this again, duplicate, draw on it, and then draw on it again. So here's the thing. When you bring friction into this scenario, it gets much harder. Just so much more cumbersome. Now, if we're going to be going 200 miles an hour, that's faster than, what did we say earlier, 95 miles an hour? If you're going too fast for the track, you're going to need friction. If you're going too fast, you're going to go to the outside of the track and off the end of the track if you don't have a barrier. So that means at this higher speed, higher than the perfect speed, your car is going to tend to go up the track. So that means you're going to need some friction to hold you down the track. Friction is going to need to act down the track to prevent you from sliding up the track. Now here's where things get more complicated, or the reason why it gets so much more complicated, and that is previously when we dealt with things on angles, things on sloped surfaces, we reoriented our coordinate system to match the sloped surface because the thing was going to tend to move up or down the surface. But that's not happening here. The thing we are not sliding up or down the surface. We're going to stay at the same height on that surface, but we are still having a centripetal force pulling you towards the center of the circle as you make your way around this track, which means we don't want to reorient our coordinate system. We want to keep the same coordinate system because any acceleration that exists is solely in the x direction. So what does that mean? That means, I'm going to get rid of this car here. That means instead of breaking our gravity force into components to meet the angles of the slope, we have to break the normal force and friction force into their components to match up with the horizontal and vertical axes. So we're going to need friction in the x direction and friction in the y direction. And we're also going to need a normal force in the y direction and a normal force in the x direction. So at this point, I'm now going to erase those original forces, and this set of forces is what we're actually going to use to create our Newton's second law equations. Now let's go back and actually read the full question. We're going to need sticky tires. We know that friction is going to be relevant, and we need tires that are sticky enough to prevent sliding. So we would like to know how much sticky should these tires be. Get rid of that and that, give myself a little bit more space, and we're going to start figuring this out. I'm just going to say friction equals mu times n, just to kind of put that up there as a reminder, because that'll come into play pretty shortly. But let's start out with the y direction. So at least in the y direction, those forces add up to 0. Ooh, we got the normal force in the y direction plus, minus the friction force in the y direction minus mg equals 0. All right, because we got normal force in the y direction up, friction's y force down, and mg down. In the x direction, that's the y direction. In the x direction, we've got the centripetal force, which, aka the net force, equals mv squared over r. So this net force, what's the force or the forces contributing to centripetal force? That is both of these. We've got 2 horizontal forces, some of the normal, hence the bank track. That's why you can go fast with the bank track, plus some friction, preventing you from sliding up the track. So we've got the normal force in the x direction plus friction in the x direction equal mv squared over r. We're going to make one substitution right away. Actually, in just a minute. Let's first figure out what are these components. Let's get some expressions for those. All right, the normal force in the y direction. In the y direction, well, the normal force looks like this. And as we talked about earlier, if the angle is 31 there, then the angle 31 degrees will also apply here. So the normal force in the y direction is the adjacent side. So that's going to be cosine. So we've got normal times the cosine of theta minus the y component of friction. So friction is like this down here, and the angle of elevation there, alternate interior angles. So there's where our 31 degrees is. So for friction, the y component of friction is the opposite side of this triangle. So we're going to use sine. So friction times the sine of theta equals mg. Move mg to the other side. If we apply the same logic to the x components, the x component of the normal force is the opposite side. So that's going to be normal times sine of theta plus the x component of friction, which will be the adjacent side. So that'll be cos theta equals mv squared over r. Now we're going to make a substitution. We've got so many variables. We've got the normal force. We got friction. We got m. We don't know m. We do know the angle. We do know gravity. So, we know velocity. We know the radius. So right from the get, we have at least 3 unknowns. Well, we're going to get rid of one of those by making a substitution because we actually know that friction equals mu times n. So I'm going to sub that in for friction. So we've got n cos theta minus mu n cos sine theta equals mg. And on the x direction, we got n sine theta plus mu n cos theta equals mv squared over r. All right. We still don't know the mass. What happens when you don't know the mass? Yeah, I think you know. So really what we got to do is, system of equations. In the end, we're looking to solve for mu. So the thing I most don't know is the normal force. So I'm going to solve this side for the normal force and then sub that in to the other side. So I've got normal force times cos theta minus mu sine theta equals mg. Normal force equals mg over cos theta minus mu sine theta. At this point, you might be saying, we already know theta. And I would say, yes, we do already know theta. And to save ourselves some writing, let's actually plug in the value of theta. It will just, there'll just be less stuff to write. So normal force is equal to mass. I'm going to leave G as G because it's just habit. Again, less writing. Cos theta, cosine of 31 is 0.86. So we got 0.86 minus mu times sine of 31, 0.52. 0.52 mu. That is the normal force. So I'm going to plug that in up here for both this normal force and this normal force. All right, so mg sine theta, which we just said a moment ago, was 0.52, so 0.52 over 0.86 minus 0.52 mu plus. So that's, that whole thing is n, and then sine of theta is 0.52. Plus mu times n, which we just said was mg over 0.86 minus 0.52 mu times cos theta, which is 0.86. And all that equals mv squared over r. Here's where mass goes away. Mass is in every term, mass cancels. Hooray, something gets easier. Let's plug in a couple more numbers. So we got 0.52. Let's see, what'll I do? I got G here. I'll just leave that there. 0.52 times 10 over 0.86 minus 0.52 mu plus mu times 10 times 0.86 over 0.86 minus 0.52 mu equals v squared over r. We know those numbers. V is 90 meters per second. We're going NASCAR speed. 90 squared. Radius of the curvature of track is 300. So let's crunch some numbers. Hey, we've gotten to a good point, actually. As ugly as this is, it's actually nice because the only thing left is mu. We only got one variable, and we can definitely algebra our way out of this. So 90 squared divided by 300 is 27. 27. On the left-hand side, we got 10 times 0.52. That's 5.2 over 0.86 minus 0.52 mu plus 10 times 0.86. That's 8.6 mu over 0.86 minus 0.52 mu. Common denominator. All right, this is getting less terrible by the minute. 5.2 plus 8.6 mu over 0.86 minus 0.52 mu, common denominator, equals 27 multiply both sides by that denominator. 0.86 minus 0.52 mu. 0.86 minus 0.52 mu. That cancels. So we got 27 distributed in 27 times 0.86 is 23.2. Distribute that into there. 0.52 times 27 is 14 mu. And on the left side, we got 5.2 plus 8.6 mu. I will add 14 mu to both sides. I'm out of space. I'm out of space. And I will subtract 5.2 from both sides. So on the left side, I got 8.6 plus 14. That's 22.6 mu. I think that's right. 14 plus 8. Yeah. Equals 23.2 minus 5.2 is 18. 18. So mu equals 18 divided by 22.6. Mu equals 0.796. Mu equals 0.8. Let's take a moment, 1, to congratulate ourselves. 2, does this make sense? Mu of 0.8. Yeah, that's reasonable. That's okay. That's feasible. Typical tire to concrete or tire to asphalt, tire to roadway, mu, it's about 1. Cheap hard tires would be 0.9. Good racing sticky tires could be 1.1, 1.15. This is well under that. So what this shows is that we have a reasonable answer. Realistic tires can do this. And so as you are racing your car at NASCAR speed around the track, you are not at the instantaneous risk of breaking traction. You have a little bit of give. If you got 1.1 mu sticky tires, you are not just at the edge of them breaking loose. You still have a little bit more to go. And so why don't we just go faster? Or, let's push the tires, let's push the limits of friction. Well, 1, you're then going to crash more and more people will die in fiery balls of death. And also, the cars, it's just hard to go faster than 200 miles an hour. How fast does the engine got to spin? And how much air resistance do you have to push through? NASCARs are notoriously pigs in the air. They just don't have the aerodynamics to go much faster. So there we go. Without friction, trivial. With friction, ouch. Thanks for watching.